Dr. D here, and today we're going to learn how molecules are like family. Namely, what polarity is, at least to molecules, and how that impacts their physical state. So come with me as we learn about the wonderful world of chemistry in Chemistry Explained. To start things off, we're going to take a look at ethanol. It has a molar mass of 46.07 grams per mole and a density of 789 kilograms per cubic meter. But we need to talk about its shape. It's hard to draw three-dimensional objects on a flat surface, so intellectual experts spent years developing the sophisticated technique of drawing triangles. Here we have a solid triangle called a wedge. And it's not called that because the C stands for cheese. It means this H, or hydrogen, is coming out of the plane or coming out of the screen, like some sort of poltergeist film or that creepy girl from The Ring. But I digress. Here we have another triangle, but scientists were too lazy to fill it in, so it looks like the beginnings of a Bob Ross Christmas tree. And if you know how to read Morse code, you'd be able to tell that this dash means that the hydrogen is going into the plane or going into the screen. If we build this with a fancy model kit, we get something that looks like a dog. But it doesn't have any fur, and it kind of has a messed up nose. Well, just don't think about it too hard, and focus on these nifty color-coded circles, where we can see the correlation between the chemistry caveman art and the messed up Poochie. Let's get back to our discussion about polarity. Here we have another chemistry caveman drawing for propane, which has a molar mass of 44.1 grams per mole and a density of 2.01 kilograms per cubic meter. If we make this with a fancy model kit, we get a lovely Kohl's back massager that you see at the checkout counter near Christmas time. And our last molecule for today, sodium fluoride, with a molar mass of 41.98 grams per mole and a density of 2,558 kilograms per cubic meter. Now, there are no model kits for ionic molecules, unless you have those little ball magnets, but I couldn't get a picture of those without getting my fingers in the shot. So you'll have to settle for these lovely circles that I drew. To compare molecules, we have to make sure that they have similar molar masses. Or if we want to compare their intermolecular forces, we have to make sure they have similar molar masses. So here for ethanol, propane, and sodium fluoride, we have 46, 44, and 42 grams per mole, which these are fairly close, and we're going to say that they're the same. It's not like we're trying to crack open the code of a gem locker or anything like that. So we can actually compare these and see what's going to happen to them and what happened, or how they behave. Now, despite them all having similar masses, molar masses, they have very different physical properties. They have very different bulk matter properties. So if we're at room temperature, which is 20 degrees Celsius, and standard pressure, 1 atmosphere, basically the normal conditions on Earth, these molecules show up in 3 different phases of matter: gas, liquid, and solid. Do you recognize any of these molecules as a gas? Like some sort of stinky stranger no other molecules wants to be around? Well, if you're thinking propane, you'd be right. The low density may have given it away, or maybe you're someone who likes to grill some burgers on the weekend. To normally know if something is a gas, we can look at its melting point and boiling point. Propane has a melting point of negative 188 degrees Celsius and a boiling point of negative 42 degrees Celsius. So if we compare that to our 20 degrees Celsius room temperature, that is higher than the boiling point. So we have gas. Propane is a gas. Moving on, do either of the remaining two seem like a common liquid? One that other molecules would like to give a big hug? If you're like me, you're probably thinking ethanol, the one that looks like man's best friend if you're a wee bit tipsy. which is fitting since ethanol is the main ingredient in alcoholic beverages. You may also recognize it as a fuel additive for your car. You may have seen E85, which is predominantly ethanol. I get regular gas, and they already turned that into E10, and if inflation keeps going up, they'll probably make it into E12. But back to the chemistry. Ethanol has a melting point of negative 114 degrees Celsius and a boiling point of 78.37 degrees Celsius, making our temperature right between both, since we're higher than the melting point, is not a solid, and we're below the boiling point, so it's not a gas, so it must be a liquid. Now, using my amazing deductive reasoning, the last molecule must be a solid. Sodium fluoride is a common additive in toothpaste and our city water, because we all love putting fluorinated molecules in our mouths. It's better than cake. Mmm, cake. Sodium fluoride has a melting point of 993 degrees Celsius and a boiling point of 1695 degrees Celsius. 20 degrees Celsius is much less than both of these, so we have a solid. Now, there are a few ways to determine a molecule's state of matter. You can look it up on Wikipedia, like most people do, but sometimes it may not be there. You can compare the temperature with the melting point and boiling point, and that's probably actually the best way to go about doing this. But this may be a lot of work. In order to get the melting point and boiling point, we have to get a solid of that molecule, then slowly heat it up until it liquefies, like a T1000 assassin, then heat it up slowly again until it boils. And I don't know about you, but my oven doesn't go up to 993 degrees Celsius. You would need something like a lava-fueled furnace to melt sodium fluoride. So another way to help determine the state of matter is to look at the molecules themselves, or at least the chemistry caveman drawings that we have here, and try to determine how the molecule will behave or interact with others. So let's take a look at ethanol, our good old family dog. Now, I want to talk about polarity. Now, this isn't referring to my brother's ex-girlfriend when she forgot her medication. Molecular polarity is when there is an uneven distribution of electrons, or electron density, like the cream in an eclair, which is always on one side. So if we look at our chemical pastry, we see it has only hydrogen, carbon, and oxygen. And we need to determine which one of these is the most electronegative, or the big boy in middle school that always ended up with everyone else's lunch money, or electrons in this case. To help size up our competition, we can use this chemistry weight chart known as the periodic table by some. If we look at the right, we'll see the most electronegative element, fluorine, Mr. Bad Leroy Brown himself. Now we can find the element that's closest to fluorine, and we'll know who's getting all the electrons. Well, oxygen is right next door, just to the left, so it is the most electronegative element for this lot, and we'll get the majority of the electrons from any element near it. So oxygen will hog the electrons from the carbon. Now the carbon is electron deficient and will pull the electron density from the hydrogens and even neighboring carbon. And that carbon will pull the electron density from its neighboring hydrogens. But the oxygen doesn't stop there. It really pulls on the electron density of this sole hydrogen. It's like some sort of crazy government pyramid scheme, and the poor hydrogens are left outside with hardly any rights to the electrons. But they stay pretty positive, or at least so I'm told. So to follow their lead, let's come up with a happier analogy. Let's say this oxygen is my lovely wife, and I'm this carbon over here. We have a discussion and mutually decide she needs a new van, so she can haul the kids around, buy more groceries, and we can go on camping trips more easily. So I give her my money, or electrons, for the new purchase. Then this other carbon, my brother, comes over and we go out for lunch. Now I'm a little short on cash, or electron density, and since he's a good older brother, he covers the bill. Now, back to our molecule here, we have oxygen with its lone pair electrons, plus some extra electrons that it has the majority of the time from its neighboring atoms. This gives oxygen a partial negative charge, which chemists represent with a negative delta symbol, because chemists are fascinated with Greeks for some reason. And if we look at the other end of the molecule, we have a partial positive charge on the hydrogens. So if we take a step back and look at the molecule as a whole, we can draw an arrow pointing towards the highest electron density, where the oxygen is. But this isn't just any normal arrow. It is a special arrow with a plus symbol on the back to indicate the electron deficient end. Now, chemists are known for being proud artists, so they'll normally simplify the matter by drawing this arrow above or below their molecule. But this serves to indicate that this is a polar molecule, because chemists like to use caveman symbols instead of writing out words. So we've determined that ethanol is a polar molecule, but what about the other two? Let's take a look at propane, because it's like the smelly kid no one wants to be around. Well, not today, my friend. We're going to figure out why propane is so gassy. So we can do the same thing we did last time, and we can determine which element is the most electronegative again. It should be a lot easier since we only have two. We have hydrogen and carbon. We can pull up our weight chart, or periodic table, and it seems like a no contest. Hydrogen is completely on the other side away from fluorine. But hydrogen is kind of special. While it often loses an electron in bonding, it can also gain one electron to get to a noble gas configuration. So it can go the distance towards the top, like Rocky Balboa, and is similar to carbon in that carbon can either gain 4 electrons or lose 4 electrons to get to a noble gas configuration, where hydrogen just has to gain or lose 1 electron to do the same. So this really is a fair fight, and there's no clear winner on who gets the electrons. But our Apollo carbon always wins the split decision, so we have our electron density slightly shift towards the carbon. And again, since there's no real winner, this is considered a nonpolar molecule. And whenever we have just carbons and hydrogens, this is always going to be a nonpolar molecule. But besides that, we also have the shape to consider. This is a highly symmetric molecule, and so even if we have our rocky hydrogens tag out with Mr. Bad Leroy Brown himself, fluorine, we can focus on the bottom left fluorines, which would pull the electron density towards the from the carbon towards the fluorine. But they effectively cancel each other out as they are pulling in and out of the screen. And yes, they are pulling down as well, but this is largely counteracted by our leftmost fluorine, who's pulling the electron density up and away from the molecule. And this happens for the whole molecule as a whole. So if we don't have a side with more electrons or electron density, we have a nonpolar molecule. So we've looked at a polar molecule and a nonpolar molecule, but what about our cake-like fluorinated fellow? Well, sodium fluoride has these symbols associated with it, sodium plus and fluorine minus. These are charges, and whenever you see a charge, you should think ions. A cation for sodium and an anion for fluorine. These species are ionic. Sodium completely gave up its electron to fluorine. Whenever you have a metal bonded with a nonmetal, there is a complete transfer of an electron. And these species experience what's called ionic bonding. Now these two charged ions stick together due to Coulombic attraction. The opposite charges attract each other, like a young Montague to a fair Capulet. So we've identified these three molecules as polar, nonpolar, and ionic. But why are they liquid, gas, and solid? Let's take a look at our polar molecular puppy, ethanol. The oxygen pulls the electrons towards it, giving it a partial negative charge and a partial positive charge to the hydrogen. The carbon minimizes its electron deficiency by pulling on its neighbors, and we end up with an overall electron distribution like this. Now there are two ways this ethanol could interact with another ethanol molecule. I'm going to start off with the more likely of the two. We can have another molecule of ethanol interact where the partial positive hydrogen can interact with the other's partial negative oxygen. This forms a very strong interaction called hydrogen bonding. And it's kind of like a marriage, and not just any marriage though, more like the one where you've been married for 60 years type of marriage. Other things may move them this way or that, but they'll be right beside each other forever. This is similar in strength to a full-on bond. Now, the other way we could go about this is where we could look at the molecule and look at it as a whole. And we'll see that we have our electron-rich side, and we can line that up with the electron-deficient end of the neighboring molecule in kind of a head-to-tail manner. And this is the decently strong interaction, but is not the same degree as hydrogen bonding. Something like a sibling. Sure, you'll be there for them and move a sofa up 3 flights of stairs, but you're not always there right next to them. Now for our gaseous nonpolar propane, if another propane is nearby, they may interact some, but this would be very, very weak. One could equate it to two strangers passing by another. They may stop and take a glance at each other, but for the most part, they're going to go about their business and stay at a distance from each other. This is referred to as dispersion or a van der Waals interaction. Then lastly, we have the belle of the ball, the creme de la creme, our ionic sodium fluoride. Now, sodium fluoride would typically make a crystalline structure in three-dimensional space, but to simplify it slightly, we'll look at just one face of a non-ionic species. Now, this sodium plus is attracted to this fluorine minus here through a coulombic attraction, making a full-fledged ionic bond. But this sodium plus is equally attracted to this other fluorine minus down here. These are both ionic bonds, which is why it is referred to as ion-ion interactions. There's a whole bunch of them. It's somewhat like people and cake. Everyone loves cake, and a great force would have to come along to take you away from your cake. So if we try to turn sodium fluoride into a gas and remove it from all the other sodium fluorides, and if we look at just this top left one, we would have to break not just this lower sodium fluoride bond, but these other sodium fluoride bonds as well. That's why the boiling point is so high for cake and ionic bonds. So how molecules interact with each other determines what physical properties they have, such as being a gas, liquid, or solid. And the strength of these intermolecular forces determines this, as we saw in 3 examples. We have the passing of a smelly stranger for nonpolar compounds. We have the close bonds of a family for polar compounds. And we have the irresistible attraction to cake for ionic compounds. And yes, I said the bonds of cake are stronger than the bonds of family. If you don't believe me, just wait till you see the blows between Uncle Jeff and Auntie T for the last piece of cake come Thanksgiving. Unless it's Grandma's fruitcake. That splits families up for a completely different reason. As always, keep thinking, and I'll see you next time. Goodbye.